Hello viewers, welcome to my channel ITJ Olympiads and AP Physics with Ambarish. And many of you might be aware that forced and damped oscillations has been added to JEE Advanced for next year. And considering that, I decided to do a problem on this. Normally, I don't focus that much on JEE main topics, but since this is a nice instructive problem and it will be helpful for advanced, I decided to write this problem. The idea can be extended to a lot more complicated problems, but for illustration purpose I have tried to keep things simple. So without much ado, let me straight away get into the problem. So here's the problem. A spherical bob of mass m and radius r is attached to a thin massless stick of length capital L. So this has got length capital L and this is a bob of mass small m, and this has got a radius r. Okay. Assuming air to be a viscous medium of viscosity eta, calculate the time period of small amplitude damped oscillations of the pendulum. So this is highly exaggerated angle, but it's supposed to be moving in a very small amplitude oscillating. Okay, and we are supposed to find out the time period of the damped oscillations, and it is given that small r is much less than capital L. Also find the maximum permissible value of eta so that oscillatory motion occurs. So you might have some intuitive feeling that suppose viscosity is very high, then it might not overshoot the mean position. It might simply come and settle over here. That's what happens. Can be illustrated through detailed differential equation theory, but here I'll use very simple logic, not getting too much into the theory of solving the second order differential equations for damped oscillations. I'll just use some standard results here. If you want, you can give it a try. I'll get into my analysis right away. Okay. So what's my strategy? My strategy will be to develop a differential equation for damped oscillations for the system, and then I'll compare the differential equation with standard differential equation for damped oscillations as given in NCERT. So I'll try to compare my equation with the standard damped oscillation differential equation, and then write the solution by analogy with the standard differential equation, and the standard solution is readily available in the NCERT. Okay. So let's do that. So let's say the pendulum is displaced by some distance x, and this angular displacement is, let us say, theta. So, and theta is very small, and L is much greater than smaller. I've used small l here, so it doesn't matter there. I had used capital L in the problem, but it's okay. And x is of course L sine theta, which can also be written as L theta. Also, using this relation x is equal to L theta, I can readily say that d square theta by dt square is 1 by L d square x by dt square. So I've just made some simplified results which I'll be using in simplifying the differential equation in the standard form. Now I can just write the torque about the pivot, and since this r is very small, I can treat it like a point mass. I can ignore the moment of inertia about its own center of mass. So tau is equal to I alpha I'm using. Of course, if its velocity is v in this direction, then it will be experiencing a viscous drag 6 pi eta rv, and I need not worry that the top point velocity and bottom point velocities are different, because L is very large, so it's as good as kind of sort of translational motion, the sphere in translational motion. So now what's the torque equation? So there's a torque due to mg, that is minus mgl sine theta. Why minus sign? Because theta is in, I've shown, in the anti-clockwise direction, whereas the torque of gravity is in the clockwise direction. Similarly, the torque of viscous drag is also in the clockwise direction. So minus 6 pi eta rv, and this distance is L, and theta is small, so no need to think about cos theta. So just 6 pi eta rv into L, and this should be equal to I alpha. So treating it like a point mass, so that's ml square is the moment of inertia, and into alpha is d square theta by dt square. Okay. Now d square theta by dt square I have already simplified here. So d square theta by dt square is 1 by L d square x by dt square. If you put it here, so 1 power of L will go, and you will be just left with ml d square x by dt square. Okay. Now you can again rearrange this, and you can divide the entire equation by L, and what do you get? So this becomes m d square x by dt square. Okay, and this term, if you take to the right hand side, this becomes 6 pi eta r, and v can be written as dx by dt. So that's what I've written, 6 pi eta r dx by dt. And then you know that L sine theta is x, and I have divided the whole thing by L, so mg by, so this becomes x by L, right? So mg into x by L is equal to 0. This is the differential equation I get for the system. And now I am posting the screenshot of equation from NCERT. So this equation is directly copied from NCERT. This is the standard differential equation for spring mass damper system. And if I compare the coefficients, so B is 6 pi eta r, and K is mg by L, and M is of course M. So that's what I've written here. And as per NCERT, the frequency of damped oscillation is simply given as omega prime, that's angular frequency, is under root of K by M minus B square by 4M square, which is also B upon 2M whole squared, you can say this term. Okay. And accordingly, time period will be given as 2 pi by omega prime, which is 2 pi by, in our case, see, K by M. So K by M becomes G by L. So that's what I've written. K by M is G by L, and B by 2M whole squared. So see, B is here, and if you divide this thing by 2M, this becomes 3 pi eta r by M. That's what I've written, 3 pi eta r by M whole squared, B by 2M whole squared this term. And so I get this solution for time period. Okay. Now for this time period to exist, of course, the term in the square root must be positive. Otherwise, the square root of negative number is not a real number, and real time period will not be defined. It turns out, if you look into the theory of differential equations, when you are getting this as a negative value, instead of oscillatory motion, what happens? The bob just settles in the equilibrium position. It doesn't overshoot the equilibrium position, so there's no oscillatory motion. So I can just make this term greater than 0. So that's what I've written. Now for the time period to be real, the term in square root must be positive. So G by L must be greater than 3 pi eta r by M whole squared, and you just rearrange this to get the inequality governing eta. So eta must be less than M upon 3 pi r into under root of G by L. Okay. So this is the solution to the problem. I hope you enjoyed my analysis, and if you enjoyed the analysis, please do remember to give a thumbs up to my video, and please share this video with as many friends as possible through WhatsApp, Telegram, Instagram, or whatever gram you use, maybe Discord. And most importantly, if you're not already subscribed to my channel, please do subscribe to my channel, because that's what keeps me motivated to do a new video almost every day. And thanks for watching the video, and I'll see you in the next one. And as always, God bless you all. Thank you.